Okay, well, there are a couple of thumbs up coming through, so we can proceed. Great. Okay, well, thanks a lot for coming through. This is my first in-person meetup in like 3 or 4 years. Anyone in a similar situation? Yeah, been a couple of years. Okay, others have been attending some. That's great. Right, so this topic is somewhat of a hot topic at the moment for relatively obvious reasons, the biggest one probably being the economic climate at the moment. That in combination with the fact that a lot of teams that are running Kubernetes and deploying a large number of applications to their clusters have a lot of traffic traversing their environments. And so that's incurring them a lot of network related costs. And so that's what I'm going to be focusing on today, but I will scope it down primarily to load balancer to pod communication and inter-pod communication. Otherwise, we'll be here for a couple of days and I'm sure everyone wants to go home. All right, just a short introduction. My name is Lukonde Mwila. You can also call me Luke. I'm a senior developer advocate for Kubernetes at AWS. I'm in the EKS service team. I'm also a CNCF ambassador. For those of you that want to connect with me, you can feel free to do so on LinkedIn, on Twitter. You can also check out my YouTube channel, but I'd highly encourage you to have a look at the Containers from the Couch YouTube channel. That's the YouTube channel for the different container service teams at AWS. Most of my recent videos get published there, but there's a lot of great material and there are more people, smarter people that also contribute to that YouTube channel. So you'll find a lot of useful material there. Okay, so I do want to start by talking a little bit about highly available architectures and applications. This is going to be fitting for the direction that we're moving in. And I'm sure you'd agree with me that running Kubernetes in the cloud is a very common model right now for relatively obvious reasons. And these are some of them. I've listed them on this slide over here. The fact that you can easily automatically provision on-demand infrastructure. You can take advantage of the elasticity and the auto-scaling capabilities in the cloud. Not to mention a lot of cloud providers also provide managed Kubernetes, which alleviates the burden for a lot of software teams of having to manage more complex components of the cluster, such as a control plane or etcd data stores. It simplifies things a whole lot. Now, running highly available architectures is widely known as a best practice. Okay, so the reason for that is you want to have fault tolerance and resilience in your environments. Spreading your architecture across multiple availability zones. If you have one zone that goes out, well, you've still got your infrastructure and your applications running in other zones. And so it essentially reduces the blast radius and it gets contained to a particular zone in the case that there's an outage in one of them. And that way your application continues to function along with the underlying infrastructure. However, as important as highly available architectures are, there is an implication, and I'll get to that. So I've spoken a little bit about the infrastructure side of things, but I want to talk about the features that Kubernetes actually provides out the box. Well, you'd have to obviously configure them, but by out the box, I simply mean native features that it has that you can use to make your applications highly available. The first one I want to talk about is pod anti-affinity rules. Anyone here worked with pod anti-affinity rules before? Okay, cool, a few people, great. So this is essentially just a scheduling constraint. The affinity rules are used to define relationships between your pods. And the scheduler actually looks at these relationships when it's scheduling pods on nodes. And based on the relationship between certain pods that are defined by the affinity rules, the scheduler will know whether or not it should place a pod on a certain node or in a certain AZ altogether. So as the name implies, anti-affinity is essentially a repelling effect. So if you don't want pods to be in close proximity with each other, and you can define that based on the topology of your cluster, whether you want that to be based on a host or a node or based on an availability zone. So if you want to spread your application out across different hosts or across different availability zones, then you can use anti-affinity rules. So this is one way of achieving fault tolerance. Now, there is a constraint with anti-affinity rules. The fact that the pods are repelling each other means that you could easily end up with one replica on a node or one replica in an AZ altogether, which isn't great for resilience, because if anything happens to that replica, then you've got your applications essentially down in that particular zone. So there's also pod topology spread constraints. And pod topology spread constraints helps you achieve the same objective. You can also achieve fault tolerance, but in addition to that, it also gives you resilience. So as you can see in this diagram over here, you have more control over the distribution. You can have multiple replicas across different zones or across different hosts. With pod anti-affinity, because they're repelling each other, you could easily end up with a situation where you have a single replica, as I mentioned. But this way, you can determine how you want them to be spread across your topology. So really, really nifty. So important to have your infrastructure highly available as well as your application. But as I mentioned, there is an implication to this. The more spread out your application is, that increases the likelihood of network traffic that crosses zones. And a lot of the network costs tied to, a lot of the costs tied to networking are often tied to cross-zone traffic costs, the high costs, that is. So you'll see in this diagram over here, we've got different applications running in different nodes, and these nodes are in two AZs. One is AZ1, the other is AZ2. And you can see the arrow between the green block and the blue block. So this is what's likely to happen, especially for applications that often talk to each other. That means that that communication is going to be crossing zones. And this is what is a significant contributor to your network-related costs. It's not the only one. The topic of network management in Kubernetes in a cloud environment is multifaceted. There's so many different areas. But like I said, we're going to scope it down to load balancer to pod communication and inter-pod communication. And in this case, I want to focus on zonal traffic. This is one major contributor. Right. So apart from teams trying to figure out how they can address the costs related to zonal traffic, some teams are also trying to solve that issue along with improving the performance of their applications. So for them, it doesn't work out for certain applications to have replicas in different AZs or in different nodes altogether. They need to have certain applications running on the exact same node for them to be as performant as possible. They're trying to reduce latency as much as they can. So we've got zonal related costs for networking. And then we've also got the requirement for some companies and some teams, maybe some of you even here, where they need traffic to not only be restricted to a single availability zone, they need it to be restricted to a specific node. And that will have two side effects. One is that it improves the performance of the application, reduces latency. And the other one is obviously the fact that there's a positive side effect of reducing your costs, because if traffic never even leaves the node, then it's never going to leave the zone. All right, so now I'm going to go through a couple of approaches that you can take to address these issues, zonal traffic and improving performance, as well as restricting traffic to the node. The first one that I want to cover is topology-aware routing. So this is a Kubernetes native feature. It's still in beta, but it does work relatively well. And in order to understand topology-aware routing, it's really important to understand the other networking components in Kubernetes. Just out of curiosity, because I know the screen is a little small. For the guys in the back, can you see? Okay, I'll try and be as descriptive as possible, but if you can move closer, that would be great. I think the people who are tuning in online shouldn't have any issues. So the isolated block on my far right, that should be your far left, that just represents a Kubernetes service. So a service is the stable network abstraction layer that sits in front of your pod replicas. Pods, once they're created, they each receive an IP address. But remember, pods are ephemeral, so they have a short life cycle, so they're continuously dying. And the issue with that is, if we're trying to get if we're trying to get traffic to our applications and we're sending them directly to pods, well, we're going to have a lot of failures. So we need something stable in front of our pods, that's the role that the service essentially provides. Now, when a service is created in Kubernetes, there's also endpoints that get created. And this is how the service actually keeps track of the IPs for the different pods. You could think of it as a table, but they're essentially endpoint slices. And each endpoint slice is like a subset of different pods, details for the different pods. So that's where it will see the name for a pod, the IP for a specific pod, the node that pod is running on, and the availability zone where that pod is running. So traffic first hits the Kubernetes service, and the service then proxies the traffic to the different endpoints. And then lastly, on every node, you've got the kube proxy. And the kube proxy consumes the information from the different endpoints. So what happens when we enable topology aware routing? That's the default flow that I just explained. Without topology aware routing, what happens is the kube proxy essentially just consumes the information from the different endpoints, regardless of where the replicas are located. With topology aware routing, what actually happens is the endpoint slice controller, which is responsible for creating the endpoint slices, adds what are known as hints. And these hints, if you take a look at this diagram over here, will essentially say that this traffic for a certain pod, if the pod is running as in zone A, should receive traffic coming from zone A. So it's essentially a way of saying, okay, this replica is running in this particular availability zone. Therefore, if the kube proxy consumes this particular endpoint, it should serve traffic coming from the same availability zone, which essentially restricts it to a single zone as opposed to having cross zone. So this is the approach using topology aware routing. The other approach to accomplish mitigating cost associated cross-zone traffic is to control your traffic using a service mesh. And the one I'll be focusing on in this talk is with Istio. Service meshes are primarily concerned with application networking. That's their main job. And they accomplish this in these four main ways that I've specified over here. Connectivity of the different applications, securing the communication between the different applications, controlling the traffic, like I'll be demonstrating later, and observing the network traffic as well. So they're very powerful tools. Now, Istio in particular has a feature known as destination rules. Destination rules are policies that you can apply to the traffic after it gets routed. So if you take a look at this diagram over here, you'll see that the arrow from the ingress gateway goes straight down to another component known as the virtual service. The virtual service is responsible for routing. But after traffic gets routed, that is where the destination rule comes in. What do you want to do with that traffic after it's already been routed to a specific destination? So with a destination rule, you can essentially apply a policy to say, I want 80% of my traffic coming from availability zone A to go to a destination in the same zone, availability zone A. And that's essentially called weighted locality distribution. It's a feature that's actually from Envoy, but Istio uses Envoy. And so the other zones essentially become failover zones, and you can change that figure. The highest, though, that you can have for a particular availability zone is 98%, of which the 1% would then go to a second availability zone and 1% to the other availability zone. The reason why you don't have 100% for one availability zone and 0 for the others is because you need to maintain failover zones as well. Okay, so those are the two approaches that you would follow to control zonal traffic. But what if you want to restrict traffic to a node? That's where the Kubernetes service internal traffic policy comes in. So in this diagram over here, I've got two microservices, microservice A and microservice B, and these are being deployed to a cluster. And if you look at the three blocks at the bottom over there, you'll see that each one has a gray block with a blue block. And well, it's not really a block, actually. I think it must be an octagon, but basically it's the Kubernetes shape, right? It's two pods, a blue one and a purple one, right? That's just representing the two microservices. And there's a dotted line between each of them. That's just to represent the fact that traffic is restricted to the node. What the service internal traffic policy actually does is those endpoint slices that get created when a service is created, it essentially then means that now only node local endpoints will be used when you apply an internal traffic policy to a Kubernetes service. So traffic can only be sent to a pod that is on the same node where the internal traffic policy, or rather, sorry, traffic can only go to a certain pod where it resides, rather. The diagram will help me out over here. So if you take a look at the third block on the far right, the gray one, where we've got that isolated purple pod. So that pod is not going to be able to receive any traffic because if I have enabled an internal service, a service internal traffic policy to it, then that means that any pod that wants to communicate with it only looks at node local endpoints. So if that purple, and it works vice versa as well. If I'd applied that to the purple pod, to the blue pods rather, then the purple one will not be able to communicate with it, because when it tries to communicate with it, traffic will drop. And I'm going to demonstrate this later, and I'm sure that will certainly help. All right, so this is going to be more of the focus of the demo, what I'm about to talk about now, a design pattern for controlling external and internal traffic, or controlling both zonal traffic as well as controlling traffic at the node. If you think about it, especially in large setups, you're going to have microservices that fulfill different roles. Some of them might need to have traffic control that is zonal level, whereas there's some where, for optimal performance, need to have traffic restricted to the node. So how do you actually accomplish both of these? Some of you might be thinking, okay, well, can't we just combine topology-aware routing with the service internal traffic policy? That's not the case. There's a constraint with those particular features at this moment. They can't be used together. So one pattern that I'm going to be proposing is using Istio with the service internal traffic policy. We're going to use Istio to control zonal traffic, and then we're going to use the service internal traffic policy to control traffic or restrict it to a node. But before jumping into this, it's really important to understand that there are three main considerations that you have to work through. The first one is to understand the role that each of your microservices plays. Is your microservice functioning as an API gateway, primarily serving traffic that comes from the public or external facing traffic, and then it proxies that into the environment? Or is it primarily just serving internal requests? So this is really important to understand before you apply the policies. And then there's also understanding the network traffic patterns, understanding how is traffic actually going to flow through your system with regards to the different components or microservices that are running in your cluster's environment. And then third is the cluster topology for your microservices. Okay, so are all microservices supposed to be running in all AZs with multiple replicas? Are there certain ones that should be co-located together on the same node? These three factors are really important to understand before you adopt this particular pattern. And I think it'll become clearer even as I go through the demo. So my demo is going to consist of three microservices. The first one is a GraphQL API. The GraphQL API is going to be serving external traffic, and it's also going to be sending traffic to both orders and products. It's functioning as a data aggregator. The reason I put the Istio Envoy proxy over there is because in the context of Istio, I'm using the sidecar proxy model, not using Istio ambient mesh. Okay, and then we have the orders API. The orders API, similar to GraphQL, also serves external traffic, but it also serves internal traffic because remember, GraphQL can communicate with orders. And then orders also communicates with products. But I'm going to have two versions of orders. And the reason I'm doing that is it'll make it easier for us to distinguish or differentiate the fact that we're seeing the traffic distribution. And you'll see that that will become clearer. So this is what I'm going to have. Two different versions of orders. They're going to be fronted by the same Kubernetes service though. And then we're going to apply weighted locality distribution to it. For simplicity, I'm calling it orders 1 and orders 2. But when I show you in Kayali, I'm not sure if everyone will be able to see just because of the size of the screen. It's going to be using the actual image tag versions. Okay, so over here, I've just got the two lists that we're going to be using. Or the feedback that we get rather when we send requests to the two different orders versions. Orders 1 is a list of orders for DC and Marvel characters. Orders 2 is a list of characters from Troll Hunters. And third is the products API. Products only serves internal requests. That's all that it does. Similar to orders, it has two lists, or rather there are two versions. And each version also has a different list of products. Again, that'll help us distinguish and be able to see what traffic distribution is actually looking like. So you can see over here with products 1, I've got a product there where 1A, the ID for the product 1A, is actually a Kubernetes t-shirt, but then 1A in products 2 is an Envoy hoodie. So that's just going to be a marker for us as we work through this. Right, so that being said, I come to my terminal. I see that it's here. That's what we want. I'm going to move this over. Okay, so the first thing we need to understand is we need to get a lay of the land. All right, so what is the distribution of our pods across the different nodes and across the different AZs? So the first one right at the top over there is, let me move my arrow over, try and help with locating things. So the first node is located in AF South 1B, and that's where my GraphQL replica is. And then I've got orders 1 and orders 2 on the same node. And the second one is a node in AF South 1A, and it only has orders 2 on it. And then the third one is a node in AF South 1B, and that's where products 1 is. So this is going to be really important to understand what's happening with the traffic distribution. But I'll keep referring to it to make it easier, because there's going to be a lot of context switching. All right, the next thing is to have a look at the different endpoints. And I'm going to start with this one over here. Let me collapse this slightly. So this is our GraphQL endpoint, and this is the query. I'm essentially aggregating data for orders and products. Let me raise this so that we have visibility of the results. There we go. And then over here is the endpoint for the orders API. And you can see there's, so the last request that I run, the list that we returned was for troll hunters characters. And then over here is an endpoint, still with the orders API, but this is an endpoint called orders products. So in this case, orders reaches out to products just so that it can return the nested data for a specific product that is associated with that order. Now, really important to remember this for the tests that I'm going to be running is only one version supports this endpoint. So when I'm executing this, you'll notice that there'll be some errors. And that means that we're hitting orders 1, because orders 1 doesn't support this endpoint. So every time we get a success, that'll be another way of noting that we're hitting the replica called orders 2. Okay. So at this point, I have no policies in place. Let me open up K9S just so you can see that. Oops. Okay, so no destination rules at this point, no Istio destination rules. Let's take a look at the services just to confirm that there are no internal traffic policies that have been updated. They're all set to the default, which is cluster, meaning traffic destined for a particular Kubernetes service should be distributed across the entire cluster as opposed to just a specific node. You can see over there let me get the arrow closer to it and scroll slightly. So as you can see over there, our internal traffic policy is set to cluster. That's GraphQL. Let's take a look at orders. Same thing, set to cluster. And then third is products. This is the one we're actually going to be changing later on. Similarly, set to cluster. Okay, so let's get to know the network traffic flow a little bit better. And for that, I am just going to run a couple of requests here in GraphQL. You might want to pay attention to the results just so you can see the changes. So there we see an order for James Lake Jr. and the product, wait, I'm in GraphQL, that's correct. And the product associated with James Lake Jr. is a Kubernetes t-shirt. If I hit send again, we see order for Bruce Wayne, and this time 1A, the product 1A is a Kubernetes t-shirt. Now we see James Lake Jr. And I'm doing this on purpose, Bruce Wayne. What does that kind of tell you so far? Sort of an even spread, right? 50-50. Every time I hit it, it keeps changing. Bruce Wayne, James Lake, so on and so forth. And that's really important to note. And if you look at the nested product, it's the same thing. That keeps changing as well. Maybe it'll be clearer if we take a look at the orders endpoint. Same thing, alternating between Bruce Wayne, James Lake. Because what's actually happening in the background is traffic is by default being proxied across in an even way. That's the default setting. I haven't manipulated the traffic in any particular way. But remember, the implication of that is I've got orders 1 running in AF South 1B, and I've got orders 2 running in AF South 1A. So that means that there is cross-zone traffic. So yes, highly available, which is good. But what's happening with my costs? It's going up, because there's so much cross-zone traffic happening. Same thing with the nested requests between orders and products. I'm getting different results for products each time because orders is communicating with the different products replicas in the different nodes that are residing in different AZs. So again, that's also ramping up costs. And this is just a 3 microservice application. So I want you to think about doing this at scale and what that's going to do with your network costs. So what we're going to do now, we've seen somewhat of an even spread. Let's add a destination rule to say that regardless of where traffic is coming from, 80% of it should be sent to availability zone A, AF South 1A, all right? And let me just to refresh our memories. I'm gonna open this again. So orders 2, as you can see over here, is running in AF South 1A. So my destination rule is going to send 80% of traffic to that, regardless of where it's coming from. And that's going to show us, so that means that we should see more results from the James Lake Jr. list, because that's this particular version of that application. I'm going to do that now. One. There we go. Let me slide this here. Okay. There we go. Let's open this and take a look at it just before we apply it so you can see what this looks like in VS Code. There's our destination rule. I'm going to try and make this as big as I can for folks at the back. Can everyone see this? Great. Okay, cool. So the part that I want you to pay attention to is over here. So you can see under the distribution property from, so this is where traffic is coming from. So I'm saying traffic coming from AF South 1A. I want 80% of that traffic to go to the destination AF South 1A, which is where orders 2 is. And I want 20% of the traffic to go to AF South 1B. And AF South 1B is where orders 1 is. That's the Bruce Wayne list, right? Scroll down a little bit more. All traffic coming from AF South 1B, I want 80% of it to go to AF South 1A. So basically I'm saying, regardless of where traffic is coming from, 80% of it go to this particular availability zone. That's just for demonstrative purposes so we can quickly see the results of what a destination role policy can do. In a real world context, what you want to do with this is to say, if traffic is coming from AF South 1B, then send 80% of it to AF South 1B. Okay, so we've applied the destination rule. I'm going to go back to orders. Let's start with the GraphQL list. So the last request returned Bruce Wayne. Let's take a look at this now and see if there are any changes. James Lake Jr., James Lake Jr., James Lake Jr., James Lake Jr., Bruce Wayne, James Lake Jr., James Lake Jr., James Lake Jr., James Lake Jr., James Lake Jr. So you see now there's more traffic to orders 2 because it resides in AF South 1A where I'm sending a majority of the traffic. But pay attention to the products list. This is still changing because there's no difference over there. That's still kind of alternating almost at an even spread between the Envoy hoodie and the Kubernetes t-shirt. So that would be the same thing even if I come to this orders endpoint over here, so this is now traffic going directly to the orders API, same thing. There's our first appearance of Bruce Wayne. The majority of it is to James Lake Jr. So we've just redirected 80% of our traffic to that particular availability zone with the destination rule. Let's take a look at what this looks like in KLE. I'm going to refresh this and collapse that. Okay, and zoom in slightly so we can see some names. Whoops. All right, let's do this. Let's say the last 2 minutes. There we go. Hide that. Oh, this is just not working with me today, huh? Okay, well, this was just for the representation. It would really help in terms of seeing things clearer, but it's not working with me. Let's stay on track. We can still get the results from Postman, which helps us. So the next thing that we need to do after having applied the destination rule is to now apply an internal traffic policy. So I'm going to go to VS Code. And this time, here's my manifest for products. I'm going to scroll down slightly. Just enable that. So I'm enabling the internal traffic policy for the products service. So that means traffic being sent to products. If any application wants to communicate with products, it needs to have a products replica on that node. Otherwise, the traffic is going to drop. Before I apply that, let's try and predict what's going to happen. I'm going to come back over here. All right. So if we send a request to the orders API directly, or specifically the orders products endpoint, we're going to see 100% error rate. Anyone want to guess why?
Because they are different nodes. It can't do local routing.
Exactly. So, but there's a little more to it, right? So remember, we're sending 80% of traffic to AF South 1A, and orders 2 does support that particular endpoint. But like you said, there's no products replica here, so the traffic is going to drop. 20% of the traffic is going to come to orders 1, but remember what I mentioned, orders 1 doesn't support that endpoint. So there will be complete failures. So each time we're going to see errors with regards to that. However, traffic that we send through the GraphQL API is going to return 100% success rate. Anyone want to guess why? So this is where the traffic map would actually really help. So it's certainly not your fault. It's on me. So this is what happens when GraphQL is communicating with orders and products. So first, the external request goes to the GraphQL API. The GraphQL API then reaches out to orders, right? Now, because of the destination policy, 80% of the requests coming from GraphQL are going to come to orders 2. So we're still going to see a lot of James Lake Jr. 20% of that traffic is going to come to orders 1, the Bruce Wayne list, right? But then when GraphQL gets a response from orders, it resolves that data and uses it to reach out to products. But because of the internal traffic policy, it will only be able to communicate with products 2. So there will be 100% success rate. The caveat is that it will never be able to communicate with products 1. It will only be communicating with products 2. So we will see the same list over and over. And products 2 is the one that has the envoy hoodie. So 80% of traffic coming to orders 2. And in terms of, because of the internal traffic policy, GraphQL will only ever communicate with products 2. Now, just to translate this to a real world context, remember, this is just a small scope. In a larger context with many microservices, you might have many GraphQLs, essentially, many API gateways that are serving external traffic, and they need to communicate maybe frequently with a certain replica that has to be on the same node. And so you can mitigate the traffic costs associated with traffic going to a GraphQL or to an orders, because remember, we applied that destination rule to orders. So you can mitigate the costs associated with that. And if you're trying to increase performance between applications and the nested requests or serving internal traffic, then the internal traffic policy can help with that. And remember, there are two benefits with that. It's not just performance, because traffic never leaves the node, it also has an impact on the cost as well, a positive effect. So let's apply the internal traffic policy and see if what I've said is actually going to happen. Should be this one here. Let me slide that. Okay. Let's confirm that in K9S. Scroll down slightly so you can see internal traffic policy is now set to local, right? So open up Postman and let's see what we get. So this is, let's start with the GraphQL. So no changes with regards to order 4. Most of them we should see James Lake Jr. But as for product, we should see nothing but Envoy hoodie, even if it's for Bruce Wayne. Okay, can everyone see that? No change. Every request is just to Envoy hoodie. And let's go to the nest. Let's go to the orders products endpoint. So remember, I said this one would return 100% error rate. Okay, so we get a 200 response. The reason we get a 200 response, but we're not seeing anything. The 200 response is because the Istio Ingress gateway is able to successfully communicate with orders. But then remember, orders then tries to communicate with products and it fails because orders 2 has no products replica on the same node as it. So the blank is because of my poor error handling in my source code. I'm not an application developer anymore, so you'll have to forgive me. But essentially there's a 503 error. And just so you can be sure that I'm not just telling you stories, let's go take a look at this. You go to orders 2. And I'm going to let's check out the logs. Make this full, scroll up. And you can see that over there, 503 error. Orders 2 is failing to communicate with products. And then if I hit this again, so most of them are going to be the blank screen because it's still 80% of traffic to orders 2. But then every now and then we'll see that 20%. And that gives us the 404 error because this is orders 1 and orders 1 doesn't support the endpoint. So the last thing I want to do is just try again and see if Kali is going to be in our favor. I'll refresh this. Oh, it's actually showing nicely now. I'm going to collapse this. Let's make it the last. There we go. That looks better. Cool. So what's happening over here? Remember, traffic first goes through the Istio Ingress gateway. And then it makes its way through to the, let's start off with the GraphQL endpoint, right? Traffic goes through the Istio Ingress gateway, goes to the GraphQL Kubernetes service. From the service, it goes to the GraphQL API itself. And then take a look at what happens. Well, like I said, orders, it'll communicate with orders first for that particular query. And then it's able to successfully communicate with both orders replicas. It's still going to send 80% of the traffic to this one, which is actually orders 2, and only 20% to that one over there. When it gets the response, it uses the response to communicate with products. But notice that it's only able to, we're only seeing one product over here, even though we've actually got 2 versions running in the cluster. That is because of the internal traffic policy. And then if we follow the path for the orders products endpoint, you'll see we're seeing a red line over here. This red line is for orders 1 because it doesn't even support the endpoint. So it's a total failure. We're seeing the green line over here because like we saw in Postman, that 200 response is there's initially successful communication because it does support that endpoint. However, there's a 503 error because when that orders version tries to communicate with products, it fails. Traffic drops completely. So if I click on this, open up pushing it, great. Let's go to traces and scroll down, show traces. And let's pick any one of these errors. Scroll down. Go to the span details and scroll down. There we go. It's just a little bit slow. So this is where we can actually take a closer look at what's happening with those requests. There we go. So you can see that traffic was sent to the product service, and we can see the exact request that was sent for products 1A, and it returned a 503 error. And we can see the same response that we saw when we looked at the logs inside of the container. So there you have it. That's a pattern for combining these two. And again, just to remember, this is not something you do just for the sake of applying these policies. It comes down to those three main factors that I mentioned. What are the roles that your microservices are playing in the larger system? And then in addition to that, what does the network traffic flow actually look like? So that's why distributed tracing is so important, but being able to understand the different requests that take place. And then third, with regards to your deployed cluster topology, how are the applications meant to run? Because all of those items or those considerations are going to influence how you apply your internal traffic policies and your destination rules. Okay, any questions?
How to split the cost if you are saying 80% traffic and 20% traffic?
Yeah.
So 50-50 answer the same cost, or 80-20 is the same cost?
Is a 50-50 the same as a 80-20? No. So that's called weighted distribution. You're essentially saying send 80% of all incoming traffic. So most of it is going to go to the destination that you specify. And so in this case, to mitigate the costs, if you say 80% of traffic coming from availability zone A should go to a replica that's in the same availability zone, then that traffic never leaves that AZ. Exactly. So it's in the same AZ, which reduces the costs. The costs are incurred when the traffic leaves that particular zone. So if you had a 50-50 split, then just like we were seeing what I started with, the even spread, then you will see relatively high costs because there's traffic essentially traversing across the different availability zones. So you want to minimize that as much as possible. But like I said before as well, you don't want to do something extreme like 98% and then have 1% and 1%, because you still need to have failover zones as well. And you want to distribute the traffic to some degree as well. Cool. Yeah.
So why doesn't the 98% work with 1 and 1? Because if you're doing round robin on ingress, it would choose every one of your replicas fairly and then split that across AZ by itself. So isn't that the most efficient way to do it? Root everything 98% and then have your ingress round robin across.
Right. So so that in that situation is just more of use case specific. So if there's a reason why you can do 98%, what I said before was that you have no 100% because you need to maintain the failover zones. If for a particular use case, again, like I think in a situation like this, you have several microservices and you're drastically trying to mitigate the costs, and there's no stress on those particular endpoints. So you need to have enough replicas as well, because that's why I spoke about the pod topology spread constraints. So if you're sending 98% of the traffic, it comes down as well to volume. How much traffic is coming in, and can that replica serve that? So if you've got auto scaling capabilities in place so that it's going to scale out, let's say with the horizontal pod auto scaler, in the case that there's a surge, then there's no issues. But again, it comes down to if you're seeing crazy costs and you want the 98% instead of like an 80%, there's no best practice with regards to an exact figure saying that keep it at 75% or something like that. Yeah. Cool. Any other questions? Yeah.
Let's say we want to do this, but how do I justify because it's going to be quite complicated, right? Then what is actually, how much cost are you actually saving? 90% I'm saving, is it like 2% I'm saving?
Yeah. Yeah, that's something that's also tricky to answer to say you're going to save this much percentage. It will certainly, with regards to zonal traffic, you will certainly save a whole lot because it's a major contributor. Again, it depends on the size of your application. I mean, if you've got a really small application and there's and you're actually even maybe just using 2 AZs, and there's minimal network traffic that's passing across the different AZs, then you're probably not going to see much of a difference. But for a team, for a team or a company that has a crazy number of microservices spread across different AZs, and there's a lot of traffic traversing the different availability zones, then you'll see a drastic difference. With this, if you're using, I'm glad you actually asked that, and you said developers, right? So the nice thing about service mesh is that it's actually meant to decouple the concerns of application networking from application developers. So in that sense, for them, they're not impeded in any way. They're not going to be touching the service mesh unless you have a particular model where your application developers work with configuring the service mesh. But in that sense, they're not impacted by that in any particular way. But something else that you said, it is complex. And that is something that's really important to consider, especially when adopting a service mesh. So I wouldn't say it's ideal to adopt an entire service mesh just to use it for destination rules. This is good if you're already using a service mesh for its many other capabilities, right? And then this would merely be an extension of that. But if you're going to adopt an entire service mesh just to use destination rules, then you're going to pay the cost in other areas: the operational overhead, the management of the other components, maintain the upgrades with regards to that, the cognitive load, etc. Thanks for asking that. You reminded me of something that I had to mention.
I have a similar question.
Yeah.
How do you know how much your interzone traffic costs you? Which tool gives you that information?
So that is going to depend largely on the cloud provider that you're using as well.
So it's not it's above Kubernetes. It's like Amazon specific.
I would say it's more of a cloud specific thing. Yeah, because that's because they're the ones essentially charging you for the cross zone traffic. And so you'd literally have to do the investigation. There are some combinations of tools you can put together to get the visibility, but even just in general cost explorers, you can see the network related costs, and you are able to see that, hey, a lot of my costs are coming from this. And so that's one of the reasons that, I was really encouraged to do this talk, is because it's something that has been coming up a whole lot. A lot of people saying, hey, my costs are surging, especially the network ones, and it's all this data transfer thing. How do I take care of this? It's one of the reasons why there's also been a lot of effort towards some of the features like topology aware routing, which is still somewhat new, and it's still in beta, but it's to save on network related costs. And then you have the internal traffic policy as well. But the internal traffic policy, like I said, the important thing to remember is that it's going to restrict traffic to the node. So just be aware of those implications. Cool. Anything else? Okay. Oh, yeah.
So you said a lot of your clients, they've asked for this. Have you gone down this route with some of them, and have you seen real results?
Yeah, so haven't gotten feedback as yet, but there was a particular one that wanted to use the combination of Istio with the service internal traffic policy. That is one that came up. But the topic itself and the topology aware routing, that one has come up a lot. Using Istio by itself, that one has come up a lot. The silence might be golden in this case when they don't get back to you. Maybe they would get back to me to say, hey, this is not working. But yeah. But usually that's why the demos are so important, because you can see the actual results, like with what I was showing you and where they were placed. You can actually see the results in that particular sense.
When you mentioned Istio the first time, you said this one is the sidecar version.
Yes.
And there's another version called
Ambient Mesh. Yeah.
What is that based
on? So Ambient Mesh, the primary difference is that it doesn't use a sidecar proxy model. So there's no Envoy sidecar proxy. So you might have noticed, and it is still relatively new. So over here, I'm in the orders container. You'll see there's the init container, but you'll see there's the Istio proxy. So with Ambient Mesh, this model has been completely removed. It's a sidecarless model. The reason for that is because there are some implications with using a sidecar model. The startup time, for example, it is more resources. And then there's also the challenge with jobs when executing a job as well. So those are some of the issues that are Ambient Mesh is essentially addressing, and making it leaner as well, because a lot of people that use Istio today, at least from my engagements and when I've spoken to other people like the core contributors, most of them want to use it for the mutual authentication and the authorization policies. So ambient mesh is essentially geared towards catering to that. And then if you want the full-blown thing to then enable or add on, as opposed to having to deal with the full-blown mesh and all that it comes with.
Sorry.
Yeah.
So for those of us who learn by doing, do you have this whole demo available on GitHub that you sort of replicate
Yeah, I'm gonna.
how the whole thing works?
Yeah.
Only bound stuff.
Yeah, no, definitely. Yes, I'm going to upload all the source code, and I have recorded this in a separate video as well. So you'll be able to watch that. I'm going to publish the video in the next couple of days, and sure we could find a way of sharing that information. But yeah. Yeah, Julian.
How do you, so it's not scope of just your KS cluster.
Yeah.
You've taken into account your RDS instance, and if you have more JDC cluster, how do you limit your zonal traffic in that sense?
Yeah, so this is now communication from pod to a database, a highly available database. Honestly, off bat, I'm not too sure. I'd probably have to investigate that and find out and then let you know. But that's a great question, because again, like I said, this is scoped down, but it's multifaceted. There's so many other domains related to the high cost, and that's another important area as well. Compute is another one. You should check out Carpenter. Shameless plug.